Swayam Prabha. Digital India. Educated India.
So, good morning. So, we will continue with instruction set architecture. So, where we left yesterday was on the RISC and CISC. We completed some insight into what is a RISC architecture and what is a CISC architecture, and what is the implication of having a RISC architecture on the compiler versus hardware and vice versa, right? So these are some of the things that we talked of. And importantly, we understood that there is something called an opcode and an operand in every instruction. Okay. Now today we will now see what are the types of instructions and how did they come into practice, etc. Okay. So every instruction that is added into a system has a background, right? There is a legacy, there is a history why that instruction essentially comes into the thing. And understanding that is extremely crucial for you to become a good compiler writer. So when you study code generation, so you did code generation in the last semester here. So one of the important things that if you want to really become a very good write a very efficient compiler, or you want to work in the area of compilation, one interesting thing that you should actually develop that interest is that you should understand the legacy behind every instruction, why this instruction is there. Okay, right. So let us go and do that. So it's going to be an interesting history. So let us see. So what are the types of machine language instructions that you can conceive of? One thing is, in a system there are, as I told you, there is memory, and inside there are registers, and then there is an ALU, and there is a control unit which controls the movement of data here and there. So this is the organization of a simple computer. Okay. Now this collectively you call this as the CPU, central processing unit. Okay. So the type of instructions could be, one of the important instruction would be data movement instructions. Okay. I move data from memory to register, register to memory, right, etc. Okay. The second thing would be arithmetic instructions, like your add, subtract, etc. Then there are certain special instructions. Right. Your data movement, I don't need to justify why you need data movement. If it is not there, you can't even move data from memory to register or register to memory. Arithmetic instruction, again I need not justify why you need an arithmetic instruction. Right? Add, subtract, multiply, these are all basic things, floating point, varieties of this. Now what is more crucial for us to understand are these special instructions. So what are these special instructions, why are these necessary, what is the legacy behind introduction of these special instructions? Once you understand that, because finally whether you do algorithms, today you said some cryptography, there is something called modular exponentiation that you will be doing as a part of it. Now there are specific instructions exclusively added to your system today to solve certain cryptography problems, right. So these are called crypto acceleration instructions. There are specific instructions that are added to your instruction set for doing media applications, like your rendering of your screen, right, doing certain computations on that. So those are called multimedia instructions, so processing your audio file. There are specific instructions that are done for doing certain database transactions. There are specific instructions that are done to do web based transactions. So today I buy as a processor which is for a server class machine versus a processor that is for a workstation class machine. What is the difference, right? There are certain transaction based instructions that could be part of your server class machine which will not be as a part of your normal workstation class machine, right. today I buy a processor for a real time system versus a normal system, right? Already we discussed this in the class. So what is the distinguishing factor between a processor that is designed for a real time system versus processor that is designed for a normal system? Huh? We discussed this in the class. We spent for 5-10 minutes on this. What is that distinguishing feature?
Depth of the circuit.
Huh?
Depth of the circuit.
Time and correctness.
No, these are the definition of what is the real difference between a processor that is made for a real time system versus a processor that is done for a normal system. Fast interrupts, excellent. Okay, so interrupt and interrupt processing instructions should be very agile in the case of a real time processor. So as I move across applications, my thrust on what I am going to do with the system changes, right? For example, the computer that I am talking today is not just one that you see on your desktop or your server or your mobile phone today. These are all equivalent for you. So whatever you do on your desktop today, your majority of the things, in addition to talking, you are able to do on the mobile phone. Okay, so these are all some classes of processors that you are seeing here. But then if you take a network switch or a router, again there is a computer there, there is a processor there. Now the type of instructions that processor will execute will be extremely different from the type of instructions that your normal fancy computing processor will do, right? For example, what will happen in a network process, can you just think of it? This is just an introduction to your networking course. Okay, can you just, Palagat, somebody can tell me what is inside a router or a switch? How many people have seen a router? Can you put your hands up? Right? All of you have seen a router. So what is inside a router? There is a CPU, there is a processor there is a lot of memory put inside the router. So there is a computing environment there. Can you just guess what are the type of instructions that processor will execute? Packet, excellent. Packet processing. Who gave this answer? Can I just, okay, good, excellent. So packet processing is a very important activity of a network processor. So what do you mean by packet processing? See, some of the things, like let us take a Wi-Fi router, right? The way a packet is transferred from this system, say, to a Wi-Fi, and from there it is transmitted to on a network, right? So this protocol is different from a wired protocol, right? So typically this is called an access point. You should have seen that, or whatever you see as a hotspot. Hotspot again is Wi-Fi on both sides, or USB plus Wi-Fi. So let us take a switch, right? So there will be one protocol, one IEEE standard which will be transmitting from here, another IEEE standard which will convert it to a wired protocol. The Wi-Fi is 802.11. So I will just note all these things because these are some things which will be useful in future also. 802.11a, b, c, g, n, so many things like that. Okay, these are all different standards. While you look at this is the wireless standard. The wired standard is 8023, if I remember correct. So IEEE, these are all IEEE standards. Now one of the important packet processing function is to convert an 802.11a packet into an 802.3 packet, right? 802.11a will have some header, 802.3 will have some other type of header. So this conversion from one format to another format is a very important functionality of a network processor, correct? So this is sometimes we call it as a portal service. What do you mean by portal service? I am porting one format to another format and vice versa. If some packet comes from the wired network to the wireless network, then I have to convert. So lot of packet processing functionalities like this form the basis, and this you will not see in a normal processor, you see it in a network processor. So when I want to design a network processor, the instruction set for it will be different from the instruction set that we see on a normal system. Okay. Similarly, can you guess of some other processors other than this? The processors that you see on what we call as this Internet of Things, right, IoTs, these are all called microcontrollers, small processors. One of the distinguishing features between a normal desktop or workstation processor and a controller is it will not have extensive memory management, etc. Okay, it will basically not even run an operating system. Okay, or there is no necessity for me to run an operating system because the functionality is very specific. Right? Of course, it's programmable, but the functionality is specific. Take some data, collect some data, do some small processing on it and send it off. Okay. So these are processors for what we call as Internet of Things. Of course, this is one major buzzword and it's going to be a major business. Okay. If time permits, sometime in the class I will give you some very excellent videos on what is Internet of Things. Okay. So Internet of Things are basically, I want to measure pollution, I put so many pollution sensors across the city, and there will be some processor which will be responsible for pinging that sensor, getting that pollution value in that area, collect all these things and send to a centralized server, and then there will be a big data analytics that you do, your machine learning and all these things, and you just find out, you get a big chart and saying this area of this city has this much, etc. Okay. So what is the processor that I am putting on those devices? That processor will basically do only one functionality. It will ping the sensor, get a value, do some normalization or something there and communicate it over a network to a server. So that's a very, very specific simple thing that it does. So normally there will not be any operating system that is executing on that. If I don't have an operating system, then many of the instructions can go on. So it will be a very, very simple lightweight processor with a few instructions. And what is the big advantage you get here? In other way, if I rephrase the question, why can't I put an Intel processor for the IoT device? Or a server class processor?
It'll be faster to just use less function.
Faster? No, I don't mean. So I am going to ping that for say once in every 5 minutes. So I'll get say 4 bytes in every 5 minutes. Power, right? So if I put the big processor there, it will consume a lot of power which I can't afford, right? So basically these things will work on some solar cell, small solar cell, and it will work. So it will be in the overall total consumption which should not exceed milliwatts, right? I can't put a watt processor there. Okay, so these are all some of the big things that come up, and every decision finally reflects in the form of an instruction set to you, because the instruction set is the interface by which I can basically access the hardware. Please understand. How do I go and access the hardware? How do I make the hardware do something? It is through the instruction set. So all my engineering decision, all my functionality based decisions, everything finally reflects in the form of an instruction set. And that is why study of instruction set architecture and understanding the legacy, some amount of history, is extremely crucial. So I just gave you a brief overview of different types of computing elements that you see in practice today and how these are basically, what are the instructions there and what are some of the functionalities there. Okay, so now let me just go into one very interesting how people made business out of this. Okay, so this is a very excellent business idea. So there was a company which made a software. Okay, this software does the following. Okay, it takes as input a compiled code of programs from an application domain. So the application domain can be say web applications, right, financial applications, networking application, cryptography applications. Okay, so one application domain it took all the compiled code in some language. Okay, it will be compiled for some x86 processor or it can be an intermediate representation. So when you do a compilation, as we saw in the previous semester, from the source language it comes to some intermediate representation and then it goes to the machine language. So I could take that intermediate representation. So just if may I had the courage to ask, what was that intermediate representation, Raghav? VM. Last time? Huh? VM. Excellent. Okay. So there was a virtual machine. So we will have some intermediate representation. So it will take that compiled code. Then it does some processing and find out what are the instructions that could make the execution of such type of codes, what are the machine instructions that could make the execution of such type of codes extremely faster. So it saw some patterns, right, it saw a lot of patterns. I will give you some example as we pro. So it saw a lot of patterns. So if there is a pattern, okay, take this data to that to this, then add this, then okay, some pattern is there. That entire pattern I will capture it as a single instruction. Okay. For example, multiply and add, okay, is one instruction that you do for lot of digital signal processing. You multiply and immediately add it. So why should I have a separate instruction for multiply and another instruction for add? Let me just say, so they are sometimes called FMA, fused multiply add. Just do it one shot. So that was a new instruction. So suppose I multiply, then I add, I take double the amount of time. If I just do one shot, multiply plus add, then that's a big, how do you design hardware for that? That is another different ball game altogether. But if I could do it in one shot, I fetch the data, I multiply and add with something, okay. This fused multiply and add can be, say, double faster than the individual multiply then followed by add. And if I do this FMA, if I want to do this multiply and add say 1,000,000 times, right, let us say each takes some 10 cycles, it will take 10 million cycles if I do multiply followed by add, while it will take only 5 million cycles if I do fuse multiply and add. So there are some basic operations which are repeated many times, right, and if I do that, if I could capture it in a single instruction and do it faster, then I get lot of advantage. So if I am going to make a DSP processor, digital signal processing processor, so all that you do here is DSP, right, your mobile phone has a DSP engine, right, it is the one which will convert your radio to digital, when you talk converting from digital to radio. So when your signal, which is an analog signal, gets converted into digital using something called ADC, analog digital converter, right, ADCs, right, this digital signal is to be processed, and vice versa when I want to send this signal back. So I need to process that signal so that it meets certain criteria. So this DSP processors have this FMA, right. You do not see this FMA in say an Intel processor, but you will see it in DSP processors. So what this particular software do is to process these instructions, find certain patterns and come out with a new instruction set, which is called application specific ASISA, application specific instruction set architecture, okay, application specific instruction set architecture. Then what it does, it immediately generates a HDL model. Last time you have all done your hardware description language, right, you described your hardware in some HDL, right. So it generates that HDL model automatically, so that you could go to the fab and make the processor. It also gives you a bootable operating system that will run on top of this HDL. So it will give you a processor which you can take in a hardware description language. It will be a soft description which you can take to a fabrication unit and make a processor. Last semester you have all seen how a HDL will be. Then it will also give you a operating system which will boot on this, and it will also give you a C compiler or a compiler in some language in which you can write code. So what you need to do to this software, give a compiled code of several applications which you intend to execute on a processor. I want to make a processor for some application domain. You take all the possible programs, give it to this fellow, that fellow will process, it will find out some common patterns, it will generate an instruction set architecture completely for your domain, exclusively for your domain. It will not only generate the HDL model, it will generate the hardware model which you can take to the fabrication unit and make a processor. It will also give you a OS which could be booted on top of it. It will also give you a compiler by which you can write programs for it, compile and run it. All these things will do, okay. So this is now the genesis of this particular software came from, please search for ASIPs, application specific instruction set processors. Application specific instruction set processors by Jason Kong et al. Et al means etc. There are many authors for that paper. This team is from UCLA, University of California at Los Angeles. Okay, just look at this, right? That's why I want all of you to do PhD. Don't go for some job after. Do something interesting, man. Now I'll tell you what is the commercial model for this. I was, I don't know, fortunate enough to sit in one committee where we purchased this for some purpose, for some Indian agency. So what happens is, once this software will be there, so you give all these programs there, then finally all this done, then it will ask you for, this is a licensed software, right? So there is one button called submit. Once I submit, then the hardware will come, the SDL model will come, the bootable software will come, and the compiler will come. And I can click it only once. After that the license will expire. Next time I can't do. And the cost of clicking once, can you guess? $10 million. Okay, so I go and click once, I will get a hardware, SDL model, I will get an operating system, I will also get a compiler for it. Everything I will get. Tomorrow I can go to the fab and make a processor, I will have my own processor industry done. But the cost of one click, Charlie, by mistake you go and click this button, that's all over. Okay, $10 million go. Okay, this is extremely important. So this is business. So this is how instruction sets have come up in life, right? So this is very, very important. Okay, so there is enough motivation for us to understand instruction set architecture, and now we have to make it, we need to really understand why should I study this. So let us first start with what we call as SIMD instructions. There are a few dozen instructions in your x86 processor, right? We will not talk more about RISC here because it's not fun. Okay, so we'll talk about CISC because I have certain beliefs, I'll tell you later. So let us talk about CISC now. So this is SIMD instruction. So what is SIMD stands for? Single instruction, multiple data. Single instruction, multiple data. So what does single instruction, multiple data mean? Suppose I say I have 100 numbers and 4 processors. So I go and say give 25 numbers to each and I say add, one single instruction to all of them, add. Each will give me a result which again one of these processors will do an add and give me an answer. So let us not bother about this part of the story, but if you look at this part of the story, okay, now I had different sets of data, right? 100 numbers, 1 to 25 was with this fellow, 26 to 50 was this fellow, 51 to 75 was with this fellow, and 76 to 100 was with this fellow. So I had multiple data, but I gave only one instruction to this, say add, right? So this is a very trivial but very important example of what I mean by single instruction add, multiple data, different sets of 25, right? So I give only one instruction, but it will act on multiple sets of data. So this is called SIMD. This is one example of what we call as parallelism. Correct? So I am exploiting the parallelism in my program. So what has happened is if I add these 100 numbers sequentially, what would have happened? I would have taken 99 additions to do that, right? here I am doing 24 additions in parallel. So, the total time required is only time required for 24 addition plus say 3 additions. So, 27 additions I can finish because I have to add these 4 numbers. Probably I will add this sequentially. Okay. So, I am exploiting, if I have 4 processors, I am exploiting these 4 processors to basically do this, right. So, what we saw as recursive doubling is also parallelism then, right. If I had one processor to do the prefix sum, would have taken order n time. If I had n processors, then it took me order log n time, right. And that is also an example of a SIMD, correct, because I did only one single instruction of adding my neighbor and making me point to the neighbor's neighbor every step. If you remember recursive doubling in a very correct way, do you all remember recursive doubling? So, now where do we see SIMD here? Where SIMD comes in place? Can you guess where SIMD can come in? You have already done one SIMD in your assignment in your 3rd semester. Where did you do? Where do you see SIMD last semester? You did L AND, right, logical AND of n bits with another set of n bits, right. You did logical AND of 2 n bits, did you do, right. So, that is parallelism, right. So, there are n bits, so 32 bits and I do 32 bits I can AND in one shot, right. So, that is an example of a parallelism. So, when we look at multimedia today, so what happens? I bring another screen on top of this, right. What happened here? Every pixel of this screen got superimposed on some pixel of this, and there could be something common if I am having this a little less. So, I am just processing. So, let me say this is some 640 cross some 320. So, 600 into 300 is what, around 1,80,000. This 1,80,000 pixels that I see here, color, is getting superimposed by another 1,80,000 here. So, what I do on each pixel today, let us assume it is 1 byte. It cannot be just because this is a color monitor, right. So, I have to represent the color and so many things there. Let us, just for our understanding, let us say each pixel is 1 byte. I want to process 1,80,000 bytes. So, I have 1 byte there, another byte here, 1 byte of which the journal, this 1 byte here, another 1 byte here. In this case I am fully masking this with that, but in case I will do half masking of this, if this screen is half of this, okay, I don't so suppose I do. Yeah, so I can see some journal here and something here, okay, you see this. So, 1,80,000 pixels I have to do processing. I have 2 pixels, one 1,80,000 belonging to this manual, one 1,80,000 belonging to that Microsoft journal, and I have to do some computations on this in parallel. This, if I do 1 byte after another, what will happen? When I press this will come like slow motion, okay, action replay, okay. But if I want fast, the moment I click on, I think it should go, and I just bring the pen here, immediately I want to see, right. So, suppose I want those type of responses, right, I am very happy. So, imagine here, one time I click this, it will take slowly, then I have to teach this course for 3 semesters, okay. So, because every time I want to show a new screen, and if I keep increasing the resolution, I want to show crystal clear things, it is going to take a lot of time. So, this is an example where I can do parallelism. Do you understand this? Where I can do parallelism, right. And I am doing the same thing, take this bit and superimpose on top of it if this is merging, or partially merging, then take some of this and some of this and show. So the same action, the same algorithm that I am executing on pixel k is this algorithm I am going to execute on pixel k plus 1. Understand this? Follow? So, this is a very, very interesting example of SIMD, and what you get out of it today, the moment I go and touch this, I am getting that screen. while I go and touch this I am getting the next screen. This is because I could do some amount of parallel processing there. The response is very quick. Do you understand? This is a very realistic example that I could give. Now for this Intel and AMD came out with what we call as MMX instructions, multimedia extension. MM is multimedia, X stands for extension. This was brought by x86 Intel. Intel and AMD were two good competitors. So when Intel came out with this, I am talking about around late 90s, AMD came out with what we call as 3D now instructions, because the 3D graphics was coming up in a big way, right. So these are all basically used for, these are all graphics and media processing instructions. Okay. Now I will just show you something that exists even today. So this is this PAD SB. So let us go into what does this mean. Please note here, so this is Intel volume, so I will not read this completely for you, there was, okay, but please note some very important words here. Oh, I can't, this will not work here. Performs a SIMD add. What do you mean by performing an SIMD add? Let us go at one of this. So I have a 64-bit operand. So this will split this 64-bit operand into 8 bytes. So it will have 8 such operations. So I will have 2 registers of size 64-bit in which I will have 8 bytes. So I will have 8 bits or 8 bytes. I will split that 64-bit register into 8 bytes, another 64-bit also into 8 bytes, and I will do operations, the same operation, like I will add the respective bytes here, right. You understand this? So this is PAD with lot of things. So there are some 3 to 4 dozen such instructions today. These are all named SIMD instructions. Now let me go and do an example of this. So I have this 64 bits, I will spread it as B0, B1, B2 till B7, and I could have another 64 bit which I will call it as C0, C1, C2 to C7, and I will put an operator here. This B0 and C0 will operate together. When this is operating, B1 and C1 will operate here, then B2, C2 and B7, C7 all together. So in one shot I can finish off 8 bytes, processing of 8 bytes, assuming that your screen was, each pixel was a byte. So I can do whatever I could do sequentially, I could do 8 times faster. Okay, are you able to follow this? Okay. Now these registers are called as MMX registers in Intel. They are named as MM0, MM1 to MM7. Right, you have a floating point registers FP0, FP1 to FP7, like that. There are, these are in addition to your general purpose registers like EAX, EBX, ECX, EDX, etc. Last class you should have done some assembly programming. Did you do that in your lab? Right, now in addition to those EAX, EBX, these are the MMX, and all these in our earlier process were 64 bits, now you have 128 bits also here. Right. Now when Intel started introducing this MMX instructions, right, please understand we started with last time we said, right, your EAX is one register of 64 bits, 32 bits, in which there are AX is the first 16 bit, AH and AL are the first and second 8 bits, right. So there was a reuse of the AH and AL register to realize AX, and there was a reuse of AX to realize EAX, right. We explained you in the first class, right. Similarly here, when Intel first introduced, they reused the floating point register for MMX. So that means your Intel processor can run once in floating point mode, and then if you want to switch to and run in multimedia mode, then you have to do some instruction to switch the state. You are able to get this? Okay. You are able to get this, right? I am first executing in floating point and I want to switch to multimedia, then I need to have a special instruction which will switch it into a multimedia mode. Okay, so that was so when a processor company wants to introduce a new instruction set, it has lot of implications, right? I need to change my complete control unit structures. I need to change my data path, etc. Right? So because I am adding a new set of registers, I need to change the hardware. Right? So the way an instruction is introduced is as follows. First, they will try and use the existing infrastructure. If it works very well, then they will make it as a they will add new infrastructure. So when I want to execute MMX instructions, the infrastructure I need is first registers, and then I need some execution units. The execution units are pretty simple because they are add, subtract, etc. But I need registers. So what Intel decided, the first step was to use the FPU register. So if you look into Intel manual, very interesting, like if you go and search for, so EMMS, empty MMX technology state. Okay, yeah. So if you read this, sets the values of all the tags in the x87 FPU tag, this floating point unit tag, word to empty. This operation marks the x87 FPU data registers which are aliased to the MMX technology registers. Please note this word, aliased. Right? Aliased means they are the same, as available for use by x87 FPU floating point instruction. Right? So if I am executing multimedia instruction, then I have to put EMMS, then I can now start using floating point. Right? So that's how, when I want to introduce an instruction into the architecture, I reuse the states. Right? This adds lot of complexity to the way. So a processor can either do MMX or it can do floating point, but not both together. And whenever I want to move from MMX to floating point, I need to store all the register values back and execute this EMMS, then do floating point, again get back to multimedia. Right? So, but these are some of the interesting things that happen in the history. Right? Another interesting thing, of course I have been telling you, so for example floating point. Floating point was not part of your processing unit at all till your 8086. So till 8086 floating point was mimicked using integer arithmetic. Yesterday I told you how you will add two floating point numbers, multiply two floating point numbers, divide, etc. Right? So this was basically done using integer arithmetic. There was no specific floating point instruction. Then suddenly it found out that engineering computations need more accuracy and precision. So the IEEE 754 standard came, and subsequently or along with it almost concurrently in parallel, Intel introduced this 8286, which is called a floating point coprocessor. So this is not part of your 8086. This is an 8286 floating point coprocessor. Now when I am starting to execute a program on 8086 and I want to do a floating point operation, the processor had the facility to check whether 8286 exists. If it exists, then it will take and get it executed on the hardware. If it does not exist, then it will mimic it using software libraries. Right? So I had to compile for an 8086 program. If I am writing floating point programs involving floating point operation, I need to compile once for 8086 with 8286 and another way of compilation for 8086 without 8286. So just because floating point was good, the technology was not matured enough to just go and immediately include in your instruction set architecture. So they made a careful decision, put it on a separate coprocessor. If that fails, only that coprocessor will fail, not the main system. Then they stabilized it over a period of time, and then today your post 8386 the systems did have both the floating point and the integer arithmetic put into the same processor. So essentially yesterday's software is today's core processor and tomorrow's hardware. So this is a transition. Yesterday's software actually becomes today's coprocessor and then it becomes tomorrow's hardware. This is also the case with graphics, right? So all the graphics was done using software. at some point of time. Then they found out, so if I want to draw a line, it will go like this slowly. Imagine here, now I want to go between this and this, every line gets drawn like this, it will take years, right. So then lot of functionalities were shifted to the graphics fellow. Like this fellow will say go and do something, the main processor will just say go do some graphics functionality, do an hidden surface elimination, the graphics processor will do. I think I mentioned in last semester course, when the main processor was running at 30 pipeline of size 30, the graphics processor was running with pipeline of 45 or 48. So the graphics processor was much more complex than the main processor, right. But initially it was software, then it became coprocessor. Today many of the graphics functionalities do come inside the chip, but it is not still part of your CPU, it's different, but it is inside a chip, inside a single chip. I also have the graphics coprocessor made, that's why it's called system on chip. That the chips you get today, the integrated circuits, we don't call it just CPU, we call it system on chips. Okay, so that is another very interesting. So as we see, SIMD was a new class of instructions that were introduced. Okay, thank you.